Hello everyone. Today we are here to present a project on an advanced approach to malware detection. Our project is titled as CAO-Based Machine Learning Malware Detection. In this project, we focus on detecting malware using system-level behavior rather than relying on traditional signature-based techniques. Now, let's move on to the presentation. Now let's look at a problem statement. Traditional malware detection techniques mainly rely on signature-based methods. These methods compare files with known malware patterns, which makes them ineffective when dealing with modern threats. For example, zero-day attacks and polymorphic malware can easily bypass these systems because they constantly change their structure. Also, static analysis only examines the code without executing it, so it fails to capture how a program actually behaves at runtime. So, as highlighted here, there's a clear need for a more dynamic and behavior-based approach to malware detection. Moving on to a proposed approach. Our solution focuses on behavior-based detection using CAO concepts. Instead of analyzing the code directly, we observe how a program interacts with the system hardware during execution. These interactions are captured using hardware performance counters, also known as HPCs. By analyzing metrics like instruction execution, cache usage, and branching behavior, we can identify abnormal patterns. These patterns are then processed using machine learning to detect potential malware. This approach makes our system more robust and capable of detecting even unknown threats.
Now moving to the CAO matrix used in our system. As you can see on the slide, we have grouped them into different categories. Execution matrix includes instructions and CPU cycles, which shows how much processing is happening. Branch matrix helps us understand decision-making patterns in programs. Cache matrix indicates how efficiently memory is being accessed. And finally, memory and system matrix include page faults and memory operations. Together, these matrices provide a complete picture of how a program behaves internally. This slide shows the overall system workflow. The process starts with user input in the form of a URL. Then we extract important features such as length, entropy, and special characters based on these CAO matrix are generated to simulate execution behavior. The data is then pre-processed and normalized before being passed into the machine learning model. Finally, the system produces a prediction along with a risk score. We use the isolation forest algorithm for anomaly detection. As mentioned on the slide, it is an unsupervised learning method. It works by isolating unusual data points that behave differently from normal ones. This makes it especially useful for detecting unknown or zero-day malware.
Now we will demonstrate how the system works. So here the user enters a URL into the input field. Once we click Analyze, the system begins extracting features such as URL length, entropy, and presence of special characters. These features help estimate the initial risk level before deeper analysis. After feature extraction, the system simulates CAO metrics based on the risk level. These simulated metrics represent how the program would behave during execution. The data is then passed to the isolation forest model for prediction. As we can see here, the system displays a final verdict, either normal or suspicious. It also shows a combined threat score as a percentage. This graph compares simulated execution metrics with baseline values. Any significant deviation from normal behavior indicates potential malicious behavior.
Now let's look at our output interpretation. Our system provides both classification and detailed analysis. It categorizes inputs as normal or suspicious, gives a percentage-based risk score, and provides graphical comparison with baseline behavior. This makes the output more interpretable and useful for decision making.
To conclude, our project demonstrates the behavior-based malware detection is more effective than traditional methods. By using CAO matrix, we can detect anomalies at deeper levels. This makes the system more accurate and capable of handling modern and unknown threats.
Finally, in terms of future scope, this system can be enhanced using deep learning techniques for improved accuracy. It can also be integrated into real-time monitoring systems and deployed in enterprise environments. Thank you. Feel free to check out our source code in our GitHub repository in the link pasted below.